Let's look at these problems. The first problem is the same type of problems that we did in the last lecture. It is to calculate Q value, but this is a different problem. Okay. In the last lecture, we were doing problems where the masses were given, the masses of reactants and masses of the product. Here, the masses are not given, but binding energy are given. And now this becomes a confusing problem in that sense. Okay. Let's try to figure out. First, you note down all the problems. These two are general problems. Okay. So this you can solve even without using the concepts that we have discussed so far. Okay. But we are going to discuss few concepts here. Okay. So we will discuss few concepts. First, we will solve it. Solving it is very easy. There is not much physics here. Okay, little bit of mathematics, calculation, and all that. Okay. First, let's look at this. Okay, if I have this nuclear reaction A plus B, this becomes C plus B. Now this is reactant, and this is product. Okay. Now Q will be delta M and C squared. Okay, this is the Q value. Now, this will be equal to mass of reactant minus mass of product, okay, times C squared. Now, if the mass of reactant is more than mass of product, that means some mass has been converted into energy, okay, then this will become exothermic. Then Q will be positive, delta M will be positive. You see, do not confuse delta M with change in mass. Because if you remember it that way, do not remember delta M as change in mass, then that is going to be confusing, because whenever we talk about change in physics, it is always final minus initial. Okay. Here, delta M is not change, because if I write change, I will have to write final minus initial. Okay. It is mass defect. What mass I had earlier and what mass I have now. Okay, so that change we are talking about. Okay, so a little bit of care is required here. Okay, and we solved many problems based on this concept in last lecture. Here, I have same type of problem, but masses are not given. Binding energy are given. Binding energies are given. Then how do I find Q value in terms of binding energy? Okay, so should I write Q is equal to binding energy of reactant minus binding energy of product? Should I write it this way, or I should write it this way: binding energy of product minus binding energy of reactant? What do you think? Which one is going to give me correct answer? You have to be absolutely sure. Otherwise, you will get opposite answer. If the process is endothermic, you will get exothermic. Exothermic becomes endothermic if you make a mistake here. Okay. So, which one we should use? Let's try to understand that with a very simple example. And we actually have done that problem already. Okay. In the previous class itself, we did that. Let's do it again. Let's do that again. Okay. Let's say that I have some nucleus here. Okay. I have some nucleus. Its binding energy is, let's say, 100 mega electron volt. Let's say that it is the binding energy. Okay. Now if I add something, okay, if I add, let's say that I am adding 10 mega electron volt of energy. I am adding it. Okay. Then what will be the new binding energy? I am adding some energy. The old binding energy, the original binding energy is 100 mega electron volt. What it means? That means I need to supply 100 mega electron volt to break this nucleus. 100 mega electron volt. Now, 10 mega electron volt is already supplied. So how much more do I need? I need 90. Okay, then that becomes the new binding energy. Okay, then the new binding energy will be equal to 100 minus 10. That means 90 mega electron volt. Okay, and if some energy comes out, okay, let's say that I have this nucleus, the same nucleus, okay, this binding energy is, let's say, 100 mega electron volt, and let's say that it releases some energy. Let's say that it releases 5 mega electron volt. Okay, then what will be the new binding energy? Okay. Okay, so here in this case it is going to increase. Okay, it is just reverse of this. It is going to be equal to 100 plus 5. It is 105 mega electron volt. Okay, this is something that you have to remember. Okay, so if energy is added, okay, that means that is Q is positive. Okay, Q is positive. Okay, then binding energy decreases. Okay, then binding energy decreases. Okay, so whatever energy I add to the system, the binding energy is going to decrease by the same amount. Okay, and if energy is released, okay, that is Q is negative. Okay, then binding energy increases. Okay, so if the nucleus releases some energy, in that case the binding energy is going to increase. Okay, now when it releases, it becomes more stable. Try to relate these things. Okay, so when this nucleus releases energy, it becomes more stable. Then more energy will be required to break it. You understand this? Okay. Now, so let's try to apply this concept, and let's look at one more case. One more case is like this. Okay. Let's say that I have one nucleus A. It changes into B, and some energy is released. I want to find Q value. Let's say that binding energy here, binding energy of A, let's say it is 100 mega electron volt. So I have one nucleus, okay, its binding energy is 100 mega electron volt. The nucleus changes into some other nucleus. It is a nuclear reaction. It changes into B, and then binding energy of B is, let's say, 90 mega electron volt. Binding energy has decreased. Binding energy has decreased. That means some energy is supplied. What do you think? Binding energy has decreased. That means energy is supplied to the nucleus. Okay, binding energy has decreased. Binding energy has decreased. Okay, that means energy is supplied. Okay, that is Q is positive and Q is equal to plus 10. Whatever is the difference, energy is supplied. That means energy is supplied. Energy is supplied. Okay, so Q is negative. Okay, energy is supplied. So it is endothermic. Energy is supplied. It is endothermic. It is endothermic process. We are supplying energy. That means what is Q? Then Q will be negative. Q should be negative. Okay. This term should be negative. We are supplying energy. Okay. That means mass of the reactant is less than mass of the product. Okay. We are supplying energy. So that energy converts into mass. That's how the mass of product increases than the reactant. And in that case, Q will be negative. Okay. So here we are applying our reverse logic. We are saying that binding energy has decreased. That means energy is supplied. Energy is supplied. That means it is endothermic. That means Q is negative. Okay. That means Q is equal to minus of 10. Okay. That means minus of. That means 90 minus 100. Okay, that means binding energy of B minus binding energy of A. Okay, that means it will be of this form. Okay, this Q value will be binding energy of product minus binding energy of reactant. Okay, this not this. They are just reverse. Okay, and memorize this point. Remember this point. Okay, so in terms of mass, this is the Q value. Okay, mass of reactant minus mass of product times C square. In terms of binding energy, if the values are given in terms of binding energy, then it will be binding energy of product minus reactant. Okay, then how do we solve this problem? Okay, let's solve it. Now the first case, Q value, binding energy of product. This is the product C and D. Okay, so binding energy of C plus binding energy of D minus binding energy of A plus binding energy of B. Okay, product minus reactant. This we have to apply. So C and D, so 60 plus 55 minus A is 80 plus 50. Okay, 80 plus 50. So this is 115 minus 130. This becomes minus 15 mega electron volt. Negative. What does that mean? Q is negative. That means it is endothermic. I need to supply energy. Q is negative. That means it is endothermic. You have to remember this. Negative Q is endothermic. Positive Q is exothermic. Now second, here binding energy is not given, but binding energy per nucleons are given. Okay, so I can find binding energy. Here I will write, this is 12 here, so 12 times 4, and second Q is 12 times 4 plus 6. 6 times 6. Okay, this becomes binding energy of product. No, product. I have to write product. First, I will write product. Product minus reactant. Okay, so product C 10. Okay, so 10 times of binding energy per nucleon. It is 7 here plus 8 times of 5 here. Okay, minus reactant. A 12, okay, so 12 times of 4 plus B 6, so 6 times binding energy per nucleon, it is 6, here it is, okay, so 70 plus 40 minus 48 plus 36, okay, this becomes 110 minus 86, that's it, okay, so that becomes plus 26 mega electron volt. Okay, this is Q value, that means exothermic. Okay, exothermic. It is a spontaneous process. Okay, exothermic, endothermic. All right. Okay. Now, okay, so the next one is pretty much does not require much physics here, not much physics, okay. We just have to calculate energy released in one reaction, each reaction. What reaction it is talking about? It is a fission of U-235. Fission of U-235. It is 92 here. Okay, uranium. In this process, so in one reaction, it releases 200 mega electron volt. This value is already given, okay. Now, how much energy is released from fission of 1 gram, 1 grams of uranium, 1 grams of uranium, okay. So this should not be difficult, okay. Number of, you see, energy released per reaction. Okay, let me write it as Q. This is 200 mega electron volt. Okay, number of atoms in 1 gram uranium N is equal to number of atoms. Okay, atomic mass is given 235. This is actually atomic. This is not atomic mass. This is mass number. But we can assume generally it happens that atomic mass is close to mass number, because if you look at the masses of a proton and neutron, they are close to 1 U. Okay, so here this also is going to be close to this. So just to simplify our calculation, let's take it as 235. And anyway, it is not given. The mass of this atom is, the atomic mass of uranium is not given. So we are going to use the same value. So if I know atomic mass, okay, I can find out number of moles. Okay, what will be number of moles? Number of moles times Avogadro number. Okay, this you know already. I am sure that you must have done such type of calculations in your chemistry class. So it should be pretty easy for you. So 1 gram over 235 times, let's take some approximate value, 6 and 10, 23. Okay, so total energy released. Okay, E, let me write it as E is equal to, okay, number of atoms times energy released per atom per reaction. So this is going to be equal to 200, okay, it's like this, 6 and 10, 23 over 235 into 200. This is 1200 approximately. It is going to be equal to 1023. Okay, this will be mega electron volt. Okay, so this is around approximately. This is approximately 5. This becomes 5 here, okay? And 10 power 29 electron volt. Okay, makes sense? Now, we can convert this into joule also. This will be equal to 5 into 1029 and 1.6 and 10 minus 19 joule. This becomes 8 and 10 power 10 joule. 8 times 10 power 10 joule. This is a huge amount of energy. Do you know this much energy comes from what amount of TNT? Okay, this is equivalent to 20 tons. 20 tons of TNT. Okay, so energy that we get from 20 tons of TNT, the same energy we get from just 1 gram of uranium. That's how much energy we get from nuclear reactions. And we actually use this to produce energy for our use. Okay, the energy that we are getting in our homes, offices, industries, it has several sources, and nuclear energy is a major source. Okay, we will discuss a little bit more about this type of reaction. Okay, let's do the other problem, the second problem. Okay, so what we calculated was it's like how much energy is, okay, so in 1 gram of uranium reaction, this much energy will be released. Okay, now let's use this value to solve the next problem here. Okay, so answer to this will be 8, 10, 10 joule. Okay, now we are going to use this to solve the other one. Now what it says, Okay, so here we have a nuclear reactor. A nuclear reactor, 500 megawatt. Okay, we have a 500 megawatt nuclear reactor. Okay, then if I ask you how much energy it is producing per second, it will be equal to 500 megajoule per second. Okay, this will be 5 and 10 power 8 joules per second. Joules per second. In 1 second. In 1 second. This power plant, this nuclear reactor, we call it as reactor. Okay, it is producing this much energy per second. Now the question is, to produce this much energy, okay, how much fuel rod I should use? And then some other parameters are given for the fuel rod. Okay, what it says is that 20% efficiency, okay, the concentration. Okay, so this energy is coming from the reaction of this uranium atom. Okay, and the fuel rod in which this uranium is present has a concentration of 20%. 20%. Okay. Question is, how much fuel rod is going to be used per day in 1 day? How many kilograms? Okay, let's try to figure out. So first, the best thing to find out is to find how much uranium is used, how much uranium is required to produce this much energy. Okay, now 1 atom, okay, 1 gram produces 1 gram uranium. 1 gram uranium produces 8 into 10 power 10 joules. Okay, 1 gram. Okay, and I need only this much energy per second. Okay, so now so uranium 235 consumed per second. How much uranium is going to be consumed per second? Okay, so this is this much joule is produced by 1 gram. So 1 over 8 into 10 power 10 into 5 into 10 power 8. Now this will be in gram per second. Okay, do you understand this? This is just a unitary method. This much energy is produced by 1 gram. 1 gram. Okay. So how many grams will produce this much energy? So 1 over this times this. Okay. I want this per second. So this much gram per second uranium is going to be used. Okay. I hope that you are not getting confused here. There are chances of getting confused. Okay. Now, so this is going to be equal to 5 over 8 into 10 power minus 2 gram per second. So 5 over 8 into 10 power minus 5 kilogram per second. Okay. Now uranium consumed per day, per second, per day. I got per second. I want to find it per day. Okay, it is going to be equal to 5 over 8 and 10 minus 5 into this is going to be equal to 86,400. Okay, this answer will be kilogram. Okay, so this will be like 10800. Okay, so 5 into 0.108. Okay, 0.54. I hope that I am doing it all right. 0.54 kilogram. I need this much pure uranium. I want to operate this To generate a power of 500 megawatt, I need to use 0.54 kilograms of uranium, pure uranium per day. Okay, per day. Okay. Now, considering 20% efficiency, considering 20% concentration, okay, not efficiency, concentration. Okay, so I have these fuel rods, they have 20% concentration. Okay, so what should be the amount of fuel rod such that I get 0.54 kilograms of uranium? Okay, so let's say that it is M, so M times 20 over 100 is equal to 0.54. 0.54, okay, that means I will get M here. M will be equal to, multiplied with 100, this becomes 54, 27, okay, 2.7 kilograms. 2.7 kilograms per second. Okay, no, per day. Per day. Okay, 2.7 kilograms of fuel rod per day is going to supply power for an entire city. Okay, a big city, 500 megawatt. It can support a big city. Okay, only half kilogram uranium per day. And compare this with the amount of fossil fuel we burn every day, coal, okay, oil, to produce such amount of energy. Tons and tons of coal will be required every day to produce this amount of. Thousands of tons, okay, will be required every day to produce this amount of power. Okay, so this is nuclear reactor. Okay. Now, we did not discuss anything about the reaction. Which reaction releases this energy? Okay, let's look at that reaction. Okay, a very important reaction. Okay? It's like this. The reaction is like this. Okay, we start with uranium 235. We start with uranium 92 235. We bombard it with a with a slow electron, okay, a very low energy electron, okay, slow electrons. Slow neutrons. Okay, energy is very small, 0.04 electron volt. Okay. So what we are doing is we are bombarding uranium 235 nucleus with slow moving neutrons, very slow moving neutrons. Okay, their energy is only 0.04 electron volt, very small energy. What happens? What happens is this uranium nucleus, it absorbs. Okay, this neutron is a neutral particle. It gets absorbed, and when it gets absorbed, the nucleus changes. Okay, now this becomes 92 and 236, and now this is a highly unstable nucleus. It's a highly unstable. This is not stable. Okay, it is going to break. It is going to disintegrate. Okay, it is going to disintegrate into several different nuclei. Okay, so let's write it as X plus Y plus neutron. Okay, plus a huge amount of energy. Okay, generally we get 2 or 3 neutrons. Okay, average is 2.5. Okay, 2.5 average. Okay, so depending on this reaction, the path of reaction, I will get either 2 neutron or 2 or 3 neutron per reaction, for one reaction. X and Y, okay, they are many combinations of X and Y are possible. Okay, there are like 90 different combinations. 90 different combinations possible. Ninety different combinations are possible. Okay, so there are 90 different paths along which this can integrate. This can disintegrate. It can break into, okay? This is what is happening inside the core of nuclear reactor. Okay, so we start with one sample. Okay, let's say that I have this sample of aluminum, uranium. Okay, there are many atoms of uranium here. Okay, we bombard it. With slow moving neutrons. Okay, it's like this. So what we are doing is, all of these are uranium uranium nuclei. Okay, a slow moving neutron hits one of the nucleus, gets absorbed. It transforms into uranium-236, which is highly unstable. It is not going to stay in this form. Immediately it disintegrates. There are 90 different paths. Okay, so there is no use of writing all those things here. Okay, you can find it in any other good reference. But anyway, that is not required. What is important to understand is that 90 different, around approximately 90 different combinations are possible for X and Y. Okay. And then these 2 or 3 neutrons are also emitted. They ejected every reaction. Okay. Now those 3 neutrons, okay, they hit other 3 uranium nucleus. Okay. So again this process continues. Now those 3 will emit 3 more like this. Okay. So this is going to hit 3 more. Okay. So it is kind of a chain reaction. Okay, this type of reaction, one reaction gives rise to the other reaction. Okay, this is known as a chain reaction. Okay, and if this reaction is not controlled, okay, then you know what is going to happen. What is going to happen is known as an atomic bomb. An atomic bomb will happen. Okay, the reaction becomes uncontrolled. It cannot be controlled, but there are ways to control it. Okay, there are ways to control it. Okay? To carry out controlled reaction, we use moderators and neutron absorbers. Okay, so we use some materials, okay, some external materials which can absorb these electrons, these neutrons. Okay, so every reaction these 2 or 3 neutrons are produced. Okay, average is 2.5. This is known as reproduction ratio. Okay, we don't really have to go into detail. I just require this reaction, that's it. Okay, but there are some important parameters. Let's look at them. So this value 2.5 is known as reproduction constant. Reproduction constant. If K is 2.5. Okay. So now if I do not do anything, I do not use these moderators or neutron absorbers, okay, it is going to be uncontrolled. Okay. Now if I want to control it, okay, I want to make it I want to use this reaction for generating electricity in a controlled manner. In that case, I have to bring down this reproduction constant. Okay. So for a controlled reaction, this K should be equal to 1. This K should be equal to 1. Okay. For controlled reaction, K should be equal to 1. Okay, it is known as critical value. Okay, so when K is equal to 1, it is called critical. Okay, and when K is more than 1, it becomes supercritical. Okay, when K is equal to 2.5, it becomes uncontrolled. Then we get atomic bombs. You cannot control. Okay, sudden explosion happens. Sudden, okay, within fraction of second, everything is gone. Okay, okay, that's how it works. Okay, let's see. So this is a reaction happening in nuclear reactor. It is known as fission. This is known as a fission reaction. Not only fission, this is known as artificial fission. Artificial, okay. We are bombarding it from outside. I'm bombarding this nucleus, then it becomes unstable, and then it disintegrates and energy is released. Okay, one nucleus disintegrating into many, more than one. Okay, it is known as a fission reaction. A fission reaction. Now, here we are bombarding it with a neutron. In many cases, this process happens naturally. Many examples. There are many examples in which this happens naturally, without any external influence. Okay, that natural fission is also known as radioactivity. Radioactivity, that is second part of this chapter. Radioactivity. Okay. So now we are going to start radioactivity. Okay. Let's see. Let's start. Radioactivity, okay? Okay, radioactivity. What is radioactivity? It is natural or spontaneous decay of one nucleus into another. Natural decay, on its own, it decays. Here the uranium 235 was decaying into several other components, nuclei, because it was bombarded. That was artificial. But here, without any external influence, it keeps on decaying on its own, naturally. Okay, so that natural fission, okay, that natural nuclear reaction, spontaneous reaction, is known as radioactivity. Radioactivity. Okay. Now, why it happens? It happens because it happens when nucleus is not stable. Okay, not stable. Why would the nucleus be not stable? Okay. Why would a nucleus be not stable? There are inherent reasons. The structure of nucleus itself is the reason behind its instability. Let me give you one thing to think about it. Think about it. Nucleus is made up of protons and neutrons. Protons are positively charged, neutrons have no charge. Okay. Now, two forces are in act here. Okay, and there is a very fine balance between both forces. Okay. One is the repulsive force, the Coulomb force. Coulomb force. What is that Coulomb force? The repulsion, the electrical repulsion between two protons. That is Coulomb force. On the other hand, so if there is no other force, the nucleus is going to be, it is not going to exist in the first place. Okay, the protons cannot be brought together in one tiny space. They are going to repel each other. It is going to break apart. Immediately it is going to break apart. Now, so some other force is involved. That force is known as a strong nuclear force. Strong nuclear force. It is attractive in nature at a certain distance. Of course, it will depend on the distance also. Okay, but it opposes the repulsive force. Okay, the strong nuclear forces, the magnitude of strong nuclear forces between two protons is same as between two neutrons, is same as between a proton and a neutron. Okay, of same magnitude. So this attractive force balances the repulsive force. Now, but the difference between them is that Coulomb force is a long range force, and 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 the strong nuclear force is a short range force. Okay, and because of that, if the nucleus becomes big, it becomes unstable. Then there are chances, there is possibility of it breaking into smaller pieces to get stability. Okay, so so this is one factor, just one factor. Okay, there are some other factors also. Let's look at the factors. Okay, factors affecting stability of nucleus. Okay, first N over P ratio. N over P ratio. What is this? Number of neutrons, the ratio of neutrons and protons. This ratio decides whether the nucleus is going to be stable or not. Okay. Now, if it is very high or very low, then nucleus is unstable. Okay, and this has been analyzed for many elements. Okay, so here we have this number of protons, and here I have this number of neutrons. Okay, this line, this dotted line here, okay, this line represents equal number for both number of neutrons and number of protons. So n over p is equal to 1. This is our dotted line, but this is not the line of stability. Okay, the line of stability goes something like this. The line of stability goes something like this. Okay, this here, this point here is A is equal to 20. A is equal to 20. Okay, so up to this point, okay, so this solid line represents line of stability. Okay, so if a given nucleus lies on this line, it is going to be unstable. Okay, now after certain number here, after certain nuclear size, okay, you see that this ratio becomes more than 1 for stability. Why do you think that is required? It is because as the nucleus becomes bigger, I need more number of neutrons to compensate for the repulsive forces between protons. Okay, that's why this line of stability, it deviates from this dotted line here. This dotted line represents n is equal to p. Okay, so as the nucleus becomes bigger, I need more and more neutrons to compensate to balance the electrical repulsive forces between the protons. That's why this line of stability deviates up to this point here. Okay, now if this ratio is too high, okay, let's say that I have a nucleus which is represented here. Okay, I have a nucleus which is here. So this is not stable. Or if the ratio is too low, okay, if I have a nucleus here, okay, then this also will not be stable. Okay, so if the ratio is very high or very low, compared to what? Compared to this line here. This is the line of stability. Then the nucleus is going to decay. It will decay on its own, naturally, spontaneously. That will be known as radioactive. It will be said to be a radioactive nucleus, a radioactive element, a radioactive atom. It is going to decay spontaneously on its own. So this is the first factor. Okay. Now the second factor Second factor is binding energy per nucleon. Okay. Higher the value, higher is stability. Okay, now if we plot this graph for different elements, okay, this is atomic number, this is mass number, and this is binding energy per nucleon, that is, this is the mass number. Mass number you know already, number of protons plus number of neutrons. Okay. Now if you do that, we get a graph something like this. This is the type of graph that I get. This is the maximum value. Okay. The maximum value of binding energy per nucleon for all the known element of all the elements that we know, that is in our knowledge. Okay. The maximum binding energy per nucleon is 8.8 mega electron volt. Okay. And do you know which element has this value? That is a very common element. It is iron 26 and 56. So this becomes the most stable element in our periodic table. Okay, the most stable element. Okay. Now, if the binding energy per nucleon is very low, then also it is going to be unstable. Okay. Now, that means if the atomic number is low here, that means the element in this part here, okay, having very low value of binding energy per nucleon, they are also unstable. Okay. Now, okay. Here, okay, and these are light atoms, light elements. Their mass number is very small as compared to this, as compared to iron here. Okay, they are heavy elements. Okay, their mass number is very high as compared to this. Both are unstable because their binding energy per nucleon is low as compared to this. Okay. Now, so what happens is these two, to achieve stability, what will happen is two light nuclei will fuse into a heavier nuclei. This is known as fusion. Two light nucleus will fuse into one another, okay, to achieve stability, and the product will be in this range. Okay, this is the range of stability. So they will fuse together and they will try to make a nucleus having mass number in this range here. So it will become stable. Here they already have a very large mass number. Okay, so they will break. Okay, so they will break and they will make light nucleus. This is a very heavy nucleus. It is not stable. Okay, so it will break into two smaller nuclei. So those two smaller nuclei will be in this range here, in this range of stability. Okay, and this process will be known as fission. Okay, so this is one very important factor, binding energy per nucleon, which decides the stability of a nucleus. Now the third very important is magic numbers. Magic numbers. Okay, what are those numbers? 2, 8, 20, 28, 50 and 82. What are these numbers? Okay, if number of protons or neutrons, okay, is equal to these numbers here, okay, then nucleus is stable. Okay, where are these numbers coming from? what is the reason behind them? Okay, the reason behind them, if you have studied the electronic configuration of atoms, the way electrons are arranged in different orbits, and every orbit has its discrete fixed energy. So we call them as states. So electrons are arranged in different states, okay, in different configurations. Out of all the possible configurations, some configurations are stable. Okay, in the same manner, the nucleons, that is the protons and neutrons, they are also arranged inside the nucleus in different energy states. Okay, and if the number of protons or neutrons is equal to one of these numbers, okay, in that case they are going to be arranged in a lower energy state, and then it becomes stable. Okay, these numbers are known as magic numbers. Okay, you should memorize these numbers. They are very important. Okay, so then the nucleus becomes stable. Okay, now, and okay, so then if it is stable, then it will not break, and if it is not stable, then it is going to decay. It is going to decay into another nucleus. Okay, how it will decay? Okay, which reactions will take place? We are going to understand that. Okay. Okay, so let's understand the decay process. Okay, decay processes. Okay, decay processes. Decay processes. Okay, first decay process is alpha decay. Okay, second is beta decay. Okay, and then the third process is gamma. Decay. Okay, we are going to study each one of them. We will solve some problems. Okay, and then we will conclude. Okay, now the first one is alpha decay. Okay, happens when nucleus is too big. Okay, Z is more than 83. This is a big, heavy nucleus. Okay, now this nucleus is not stable. Okay, it is going to decay. And when it decays, let's say that I have this nucleus here. Okay, happens when nucleus is too big. Okay, so I have this nucleus here. It is its mass. Okay, atomic number is Z and mass number is A. Now this is going to decay through this path, which is alpha decay. Okay, it will decay into another nucleus. Okay, plus alpha particle. Now what is an alpha particle? Alpha particle is the helium nucleus. Okay, so its number of protons is 2, and this mass number here is 4. Now if I balance charge, this represents charge, and this represents mass. Okay, if I balance charge and mass both, in that case this is Z. If this is 2, this should be Z minus 2. Okay, and this will become A minus 4. Okay, so when beta decay happens, okay, in beta decay, no, not in beta decay, in alpha decay, okay, atomic number, okay, decreases by 2, and mass number decreases by 4. This is known as displacement law. This is the displacement law corresponding to alpha decay. Why do we call it displacement? Because when you see this element has certain place in periodic table. When alpha decay happens, its position is going to change. Now it will come 2 places behind it. Okay, so it is going to be displaced in the periodic table according to this law, and that's why it is known as displacement law. Okay. So this is alpha decay. When it happens in a very big nucleus, when the nucleus is too big, like atomic number more than 83, all of them decay through this alpha decay, this process. Okay. Now second is beta decay. Beta decay. Okay. N over P is too high or too low. It is very high, okay, very high or very low. Okay, now first case, okay, N over P is very high, N over P is very high. Okay, then okay, so let's understand it this way. This ratio, this decides stability. N over P, neutrons are more than protons, away too much, away too more than required. Okay, now I want to get stability. Then what do I want? I want this number to be reduced because it is too high. This value is too high. I want it to be reduced. And that actually happens. What happens is when n by p is very high, then a neutron changes into a proton. Okay, beta particles electron are emitted. They are emitted. Okay, so it's like this. A neutron, I have a neutron here. It is going to change into a proton. This is charge. This represents charge. This represents mass. Mass of neutron, mass of proton, approximately same. Okay. Plus, I have to balance the charge also. Okay. So this becomes electron -1 and 0 here. Okay, electron. This is one electron here. Okay, plus another particle is emitted. Okay, another particle is emitted, which is known as an antineutrino. Antineutrino. Okay, this is electron. Okay, also called beta particle. Okay, beta minus. Okay, so we represent it like this. Okay, we also write it like this: P plus electron plus antineutrino, or a neutron changing into a proton plus beta, negative beta. This is known as negative beta decay. Okay, plus antineutrino here. Okay, so note it down. So we have three types of beta decay. 3 types. Okay, this is the first type. When n over p is very high, okay, it is negative beta decay. It is negative beta decay. Okay, electrons are emitted. Now, what will be the displacement law? Displacement law corresponding to this decay. Okay, let's see what is the displacement law. Okay, in beta negative beta decay, okay, it's like this x, it is z here and a here. Now this changes into y plus beta. beta minus, okay, plus antineutrino, plus there can be some energy involved, okay. Almost always the energy is involved, okay, in every nuclear reaction. Okay, so we represent everything like this, okay. Now let's balance the charge and mass, okay. This represents charge and this represents mass. Okay. Electrons have very small mass, so since neutrons and protons are involved here, so in this involvement we can ignore the mass of electron, okay. So we see that the masses are already balanced, okay. So there is no need to change this. Now here, or anyway, this mass number, okay, a neutron becomes a proton. I have in a nucleus, I have some number of neutron, some number of proton, okay. A neutron becomes proton, proton number increases, that means atomic number increases, it becomes Z plus 1. Atomic number increases, but the number of neutrons plus protons, it remains same, okay. In a bag, I have 5 red balls and 5 green balls. If one red ball changes into a green ball, then the total number of balls remain the same, okay. That means this mass number is going to be same, but now I have one more proton. Number of neutrons has decreased by 1, number of proton has increased by 1. So this atomic number will increase. Okay, so atomic number increases by 1. Okay. I will write here I will write increases by 1, and mass number remains same. Okay. What is this? This is negative beta decay. What are negative beta particles? Electrons. Electrons are negative beta particles. Okay. What other particle is emitted along with negative beta? They are known as antineutrino. Antineutrino. If you look at the charge and mass balance, okay, what do you expect the charge and mass of this antineutrino to be? They are chargeless. Note down, they have no charge and they have either zero mass or very small mass, even smaller than the electron. Okay, antineutrino. Note it down. Now the second one is positive when it is too low. The second, okay. Let's look at the second case. Okay. Now second case, N over P is too very low. Okay. Very low. Okay. Two processes happen. Okay. Positive beta decay, first process, and then electron capture or K capture. Okay. Are you getting the point? Nucleus too big, alpha decay. Then N by P ratio very large, negative beta decay. N by P ratio very small. Then two possibilities. Okay, one is positive beta decay, the other one is known as electron capture or K capture. Okay, both are competing processes. Okay. So both can happen. Okay, either this or that will happen. Okay, now first case, positive beta decay. Now what is happening here? N by P is too low. So N is number of neutrons is very small. Smaller than required. Or we can say number of protons is more than required for stability. Okay, then what happens is a proton decays. A proton decays into a neutron. Okay, so it's like this: a proton, okay, it decays into a neutron. Okay, a positive charge here, a zero charge here, plus positive beta particle. Positive beta particle, okay, plus neutrino. They are known as neutrino. Neutrino plus some amount of energy is involved. Okay, this is proton, neutron. This is known as positron. Positron, okay, antiparticle of electron. Okay, it is also written as E plus. E minus is electron, the normal electron. E plus is the antiparticle of electron. It has same mass but opposite charge. Okay, it is also known as a positive beta particle. Positive beta particle. Now, what will be displacement law? Displacement law, what it will be? I have this element Z and A. Okay, it is converting into Y plus this beta particle is emitted. Okay, let's look at this conversion here. Proton getting converted into neutron. Number of proton, number of neutron, it remains same. Okay, so mass number is going to be same. A proton is converting into a neutron. Okay, proton is decaying, so number of proton is reduced. So atomic number is reduced. This becomes Z minus 1. Well, that's how it works. Plus this neutrino plus some heat here. Okay, so what is displacement law? Mass number remains same. Okay, atomic number decreases by 1. Mass number remains constant. Okay, remains constant. Remains same. Okay, remains same. Okay, you can also do it this way. Okay, if you balance the mass and charge here, okay, this is charge Z. Okay, here the charge is plus 1, plus E, plus 1. Okay, so here it is plus 1. So if you balance the charge, okay, then it should be Z minus 1 here. Okay, now what about these two particles, neutrino and antineutrino? Okay, neutrino, let's write here, let me write it here, neutrino and antineutrino. Neutrino, antineutrino, okay, chargeless, no charge, okay, zero or very small mass. Okay, they are elusive, or they are also known as ghost particle. Ghost particles. Okay, very weak interaction with matter. They do not interact with matter, or even if they interact, the interaction is very weak. So it is almost impossible to detect them. Okay, the neutrinos can pass through this entire Earth unaffected. Okay, it appears as if for neutrinos the whole universe is transparent. They will never feel they are passing through which material. Okay, they can pass through iron, lead, the densest of materials very easily. Okay, because there is no interaction, they are not going to be affected. Okay, so they are known as ghost particles. Very elusive, very difficult to detect them. Okay. Okay, so this is displacement law regarding this positive beta decay. Okay, now the third, the competing process. The competing process is electron capture. Okay, K capture, also known as K capture. Okay, this is the competing process, K capture. Okay, when one of the k shell electron is captured by nucleus, then what will happen? A proton will capture one electron and then the neutrons. Okay, K capture. Neutrons and then the neutrinos here. Okay, proton, the innermost electron, the closest electron. K shell is the closest shell. Okay, so this is very low, n by p is very low, that means positive charge is very high with respect to what is required for stability, of course. Strong attractive forces. It captures one of the electrons. One of the electrons is captured, okay, by the nucleus. Then it merges with proton. A proton converts into neutron. Okay, the number of protons decreases and this increases. Okay, so this becomes little high. Okay, it is very low. It becomes little higher. It becomes stable. Okay, so now what will be displacement law here? Okay, Z and A. It converts into Y plus I am getting this neutron here. Okay, neutron. A neutron. Okay, neutron will be 0 and 1. Neutron plus this neutrino plus energy. Energy is always involved. Okay, and okay. Now, number of neutrons, protons, it remains constant, does not change. A proton converts into a neutron. So the proton number decreases. So atomic number decreases. It becomes Z minus 1 here. It becomes Z minus 1. Okay. Z minus 1. And then this remains almost, this remains same because the mass number is same. Proton converting into neutron. Mass number is same. A neutron is ejected. K shell electron is captured. Okay. Now, when K shell electron is captured, then what will happen? When K shell electron is captured, then what will happen? Okay. A vacancy is created. When K shell electron is, okay, I think this is not how it is. Okay, I think I need some correction. Why? Because this neutron is not coming out. It appears as if the neutron is ejected. Neutron is not coming out. The neutron remains in the nucleus. Okay, so this is not correct. The neutron is not emitted. Rather, this electron is captured here. Okay, so this becomes Y. Z minus 1 and A. Okay, plus. You see, this neutron is not emitted, it remains in the nucleus. Okay, let's come back to this point here. So one of the electrons is captured, a vacancy is created, okay, and that vacancy is filled up by the higher shells, higher energy shells. What will happen? We have studied that in the last chapter. X-rays will be produced. Okay, when that vacancy is filled up by higher shells, then X-rays are emitted. Okay. Okay, so I think we have taken too much time. Okay, let's complete this quickly. Okay, now so alpha decay, beta decay. The third one is gamma decay. Okay, gamma decay. Okay, the third one is gamma decay. Okay, it follows, first of all, it follows alpha and beta decay. First of all, it never happens independently. It is always a byproduct. It is subsequent to alpha or beta decay. Alpha, it follows alpha or beta decay. Alpha or beta decay. Okay. Now what happens is in alpha beta decay, the daughter nucleus is produced in energetic, excited state. When nucleus comes back in ground state, then high energy photons are emitted. They are called gamma rays. Gamma rays. What is happening here? Like we have states, energy states in the orbit of atom, orbit of electrons. Exactly same way, inside the nucleus also, the nucleons, the protons and neutrons, are arranged in different energy states. Now whenever this happens, alpha decay or beta decay, either one, or both, the daughter nucleus that is created, it is created in energetic state, in excited state. And as we did it in Bohr's atom, that the excited states are not stable. When electron jumps from ground state to excited state, it is going to come back. Similarly, this also is going to come back. And when the nucleus comes back in the ground state, then the photons are emitted equal to the energy difference. Now, in the energy states of electrons, the difference in energy states is of the order of electron volt or a few kilo electron volt at the maximum. We studied in X-rays that the energy differences are between two states are of the order of kilo electron volt. In case of hydrogen atom, it is of the order of electron volt. But here, the energy states of nucleus, you should note down this point. The energy states of nucleus are of the order of mega electron volt. So these photons which are emitted, they have the energy of the order of mega electron volt. So these they are known as gamma rays. Gamma rays are highly energetic photons. They are also EM waves, but highly energetic. They have energy even higher than those of X-rays, even the hard X-rays. The energy of gamma rays will be thousands of times more than the energy of even the hardest X-ray. They are of the order of million electron volt, mega electron volt. So it's like this. So I have this nucleus. It is going to decay into through alpha decay. Let's say this is Y. This is Z minus 2 and A minus 4 plus alpha plus Q. Now this is created in excited state. So we use this symbol. Note this down. This is a symbol. It's a symbol. This is star. This is star represents that this nucleus is in excited state. This is known as a daughter nucleus. A daughter nucleus. This is a parent nucleus. Parent nucleus undergoing decay process becomes a daughter nucleus. Now this daughter nucleus is in excited state. So now this is going to come down. Now when it comes down, it comes into its normal ground state. everything remains same, mass number, atomic number, everything, okay, plus this gamma rays are emitted. Okay, so this gamma decay follows, it is not a separate process, it follows alpha and beta decay. Okay, that's it. Let's solve a few simple problems and then let's close this. Okay, few simple problems, and then in practice sheet you are going to find many. Okay, in the problem sheet. Okay, just few. First question, identify X. Okay, I'm going to write just few simple problems. Okay, it is polonium, it is 215 here, 215, and then 84. It changes into some component plus alpha here. Some nucleus, it is not known. Okay. Second, this X here, it changes into iron, 26, 56, iron plus let's say this electron here plus neutrino. Electron, with electron we get anti-neutrino. Okay, so this will be anti-neutrino. Okay, and then third, okay, this X changes into nickel, 28 and 65 plus gamma. Let's do just this. Okay, I'm sure that you will be able to find out. It's not a big deal. Okay, no big deal. Very simple problems. Okay, now a nucleus undergoes 8 alpha and 6 negative beta decay. A nucleus undergoes 8 alpha and 6 negative beta decays. Okay, what is daughter DA? Okay, okay, all right, daughter nucleus. What is daughter nucleus? Okay. So which nucleus? Nucleus is not given. Okay, so let me write here. Let me give some value here. Okay, okay, it's like this: X 92, 238. Okay, so this nucleus, it undergoes 8 alpha and 6 negative beta decay. What is daughter nucleus? Find the daughter nucleus. That means its atomic number and its mass number. What do you think it is going to be? Okay, so let's do this quickly. It's been a long class, but that's fine. We are at least able to complete one topic. Next, let's say we are going to start laws of radioactive decay. At what rate decay? Okay, all of this is natural decay. All of this is natural decay. Okay, natural. At what rate it is going to happen? Per second, how many atoms will disintegrate, and all that. Okay, so they are known as laws of radioactive decay law. Next, let's say, okay, let's complete this here. This is alpha particle. That means this is 2 and this is 4. Okay, that means this will become 82. Charge has to be balanced, mass has to be balanced. This will become 2, 1, 1. That's how we do it. Okay, we also got the same thing. Now electron here, negative electron. That means its charge is going to be -1 here and mass is going to be 0. That's how we do it. This is anti-neutrino, chargeless, massless. Chargeless, massless. Balance the charge. So this should be equal to 25 here. 25 here, and then this should be 56 here. That's it. That's how we balance charge and mass both. Okay, here. Gamma radiation. A single nucleus resulting into a single nucleus and gamma rays. That means it is the same nucleus. Okay, this is 28 and 65, and this is in excited state. So I will mark this here. This is important. This is important. This is a symbol to denote a nucleus in excited state, energetic state. Now, 8 alpha and 6 beta decay. Now, alpha decay. alpha decay. What is displacement law? Okay, Z and A. So this becomes Y, Z minus 2, A minus 4 plus alpha 2 and 4. Okay. So this reduces by 2, this reduces by 4. Okay. And then I have this beta, negative beta decay. Negative beta decay. So this is A, Z and A. Let's say it is X here. It converts into Y. Now this becomes more than, increases by 1. It remains the same. This is electron. Beta negative is same as electron. Okay, charge is balanced. This is minus 1 here. Z plus 1 minus 1. It becomes Z. Okay, so now, so 8 alpha. Okay, change in. Okay, so here, okay, what will be A dash, or let's write Z dash. It is going to be equal to 92 minus. Okay. Now, because of alpha decay, this is atomic number, it is going to decrease by 2 for 1 alpha decay. I have 4 alpha decay. So, 8 times 2, 8 alpha decay. Now, because of this beta decay, it is going to increase by 1. Okay, I have 6 beta decays. So, plus 6 times 1. Okay, so this is 92 minus 16 plus 6. This is 82. Okay, what about A dash? It is going to be equal to 238 minus. Because of alpha decay, this is atomic, the mass number is going to decrease by 4. So because of 8, it becomes 8 times 4. It is going to decrease. Because of negative beta decay, there is no change in mass number. Okay, so that's it. Okay. So this is 238 minus 32. It is 206. Okay, that means finally I will write it like this. This is X, 92, 238. Okay, I have this thing here. It changes into Y. It becomes 82. And this is 206 plus 8 alpha plus 6 beta. Plus some energy is always involved. Okay, that's how it is. That's how we solve it. Okay, do few more problems from the sheet, and I'm sure you will enjoy doing problems. They are very simple type, very simple type. Okay, so let's conclude here. Next lecture, laws of radioactive decay.